colleague from the University of Oregon, Art Farley, and Isolde Adler from the University of Frankfurt. Okay, so here's a quick overview. I will show you the result, which is not a big result, it's just first result of the type. What are the obstructions in terms of vertex minors to a small class of graphs, the graphs with linear rank with 1. And my reason for doing it is that I have a chip on my shoulder with respect to the class Pn and P, so complexity of computation. Well, our work on width parameters obviously has to do with the parameterized, more with parameterized complexity. You've heard it before and you'll hear it again, of course. And then what the structure of graphs is, in my opinion, and then, of course, just mentioning dynamic programming as dealing with graphs of certain structure, and then I'll tell you a little bit about things that you already know, of course, with parameters of graphs and the embeddings that vertex minors, Zdeněk already told you, and then I will show you more about this obstruction to linear rank with 1. This is the result, and I could thank you now and finish it, but we have 3 graphs which we call cube, and this is a half cube really, because you can think of the other half of the cube being imposed from the top, and the net graph, this triangle with whiskers, and then the cycle. So these are vertex minor obstructions to rank with 1. And everybody agrees that NP completeness is most probably implies exponential complexity, so there's a little joke that NP means non-polynomial, but of course it means non-deterministic polynomial. And yesterday Hans had this nice emoticon of sad face, rather than big O of n is sad face of n. I couldn't find it in my computer, because I didn't have my computer, because my computer crashed when I was finishing. But of course, that's what I'm talking about, right? And so I said sad face because this big O, of course, implies sometimes constants that are astronomical. So the W hierarchy, which includes fixed parameter tractable problems on the lowest level, deals with this. And here, you know, separation of concerns, the function of m and function of k. We can separate there, and if one is polynomial, while the other may be hyper-exponential, then we have, as long as k is fixed, we have fixed parameter tractability. So that was the complexity of computation part. Now, the structure of graphs, what do we mean by structure, or what do I mean? Of course, everybody has her or his favorite view of things, and some type of grammars, hierarchical graphs to case structures, modular decomposition, something that have a parsing structures. So we talk about classes of graphs that have parsing structures, and examples are series parallel graphs, graphs on the tree with complement reducible. That's actually my favorite class of graphs for certain reasons, PQ graphs. So there is a parsing structure, and then optimization. So grow with graph classes, optimization, and with parameters. So I hit all of them here in the quick introduction to things that we all know well. Recursive structure of solution, when dynamic programming principle applies, gets us efficient computation by a bottom-up traversal of the tree of subproblems. And if this tree is we can use the parsing tree of the class of graphs as this tree of dynamic programming, and that's how we get the efficient computation. So now, with parameters, and we know that at the beginning was bandwidth, at least for me, that was something surprising, and then we come we see tree width and path width, which actually it's an interesting linear structure imposed on tree width and then branch width and click width and rank width and linear rank width, which similarly relates a more linear structure, parsing structure than rank width, as path width has the linear rank width. Linear parsing structure when we think of tree width. And then embeddings, and I like G and H, maybe slightly reverse that you normally use because I'm thinking of guest and host. So we embed guest graph into those then, and we map elements of G into elements of H, and there are different embeddings, of course, topological. Zdeněk talked about, actually, he hit two of them in the minor embeddings we're talking about yesterday, so we all know what all this is about. And then I finally got to graph classes, obstructions for the graph classes which are closed under certain one of those embedding operations. And the minimum also, if the graph classes are closed under the embedding operation, that then we have a border somewhere there which separates everything else from graphs in the graph classes, and minimal under this operation graphs just above this border are called obstructions. And again, we know obstructions in minor sense for outer planar graphs and planar graphs, which are also topological minor obstructions, the famous Kwiatkowski theorem, and the tree with three graphs, which is so 1, 2, 3. We were talking about Hans, I believe, mentioned this yesterday, that for 1, 2, and 3 that there are those very small classes of very small sets of obstructions, and for tree with 3 is K5 and double wheel on 4 vertices, and this minor of 8 vertices, which looks like this. Again, I couldn't draw it easily in not PowerPoint, so this is M8, and M10 is the prism of on 10 vertices. So that's a quick reminder what there is in terms of small obstruction sets. Already for what was it? Langston and somebody else had an obstruction set of 110, explicit construction for 110 obstructions. At the moment I cannot recall the class they were obstructing were. So here we came up with the first small set for linear rank with 1, which is the graph, the cycle on 5 vertices, and the net graph, and this half-cube graph. And so this is a quick description of our results. And now, just a too long, possibly, introduction to the linear rank with 1, you think, but somehow unifying what I know about width parameters. We have tree decomposition and the cubic tree with internal nodes of degree 3, and leaf nodes are labeled by elements of the graph, and then each branch of the, so I use nodes and branch just so that there's no confusion. Each branch of the tree partitions the graph elements that label the leaves into 2 blocks defined by a set of disconnected leaves, and then we evaluate the width function on this partition, and maximum valuation over all branches determine the width of decomposition, and minimum width over all decomposition. Then I already mentioned it, but I do it again, so if you missed it, again, determines the width of the graph. So here is, and we said that the tree is just a cubic tree, so it can be of any shape, but if we have linear structure caterpillar of this decomposition tree, and there is a body, and the leaves are just one pendant vertices from the body, and it is a cubic tree, so this is a caterpillar, and the linear width is defined by the rank of the cut determined by each of the branches of the decomposition tree. So leaves of the tree decomposition tree are labeled by vertices of the graph, and width of the branch is the rank of the adjacency matrix of partition. Here's a quick example. And what do we see here? The graph that I showed you before has 6 vertices, and then we decompose, or the tree decomposition of this is as shown below, and the first non-trivial branch, there are 3. There's 3 of them, the green, the purple, and the green again, and we look at the adjacencies between vertices on the left, so to speak, and vertices on the right, and the first green branch has all zeros and something else. So the rank of this is 1, and the second one has 1, 0, 1, and 0. So again, the rank is 1, and so is the second green branch of the tree. So we see that this tree decomposition has width 1, and therefore this is since the tree decomposition is a caterpillar, the graph on the top there is the graph of linear rank with 1. And then Robert Gagnon had a very nice characterization of graphs with linear rank with at most 1. It is the same as thread graph. So thread graph is the concatenation, so to speak, of blocks whose thread edges form a path. A thread edge, so let me define a thread block. It has a so-called thread edge and an ordering of vertices. So here we have this linear structure which imposes a linear ordering of vertices, as other linear width parameters also have. So to speak, the vertex layout. And we introduce those two labels, L and R, just to make things visual, and we label the vertices of the graph by L, R, or L and R, so that V1 is labeled R, Vn, V1 is labeled. Oops. Here it is. Vn, in this case 6, is labeled L, and L and R indicate left and right, as you may have guessed, and depending, so that the vertices labeled L are connected to the preceding the vertices labeled R, or having R in the label. So what I see to the left if I'm labeled L, and what I see to the right if I'm labeled R. And here is a quick recapitulation of Vertex Minors R, and Vertex Minors map vertices of G into vertices of H. So if we're thinking of embeddings, and then we use this embedding modulo local equivalence. As Zdeněk said, local equivalence is when we do the local complementation at a vertex. So here is this G star V. Here's an example. Again, you've seen it before, you see it again. We have cycle C5 and complement, oops, sorry. Complement adjacency here to get this. Oh, thanks. And then if we complement the same vertex again, and then we go back, of course, if we do local complementation with respect to one of the vertices of degree 3, we get the same graph, so we do it on the third one, and we get the third graph. And these are all locally equivalent graphs to C5. So just to complete our menagerie, so to speak, of graphs, here are the graphs locally equivalent to the net graph, and here are the graphs locally equivalent to the half-cubed graph. So what we are saying is that none of these graphs, or all of these graphs, are the obstructions to linear rank width. Rank width 1. And of course this is easy to show, but we also have to show that there are no more than these graphs. There are obstructions to linear rank width 1, and here is a logical argumentation that obviously C5 and Q are obstructions. There are obstructions connected, and in an obstruction, no cut vertex separates more than two components. And then we go through some case analysis that I will not bore you with, and case analysis is based on the number of pendant vertices, and we conclude that these are the only obstructions. So hence our result, and that's the end of my talk. Thank you.
Other questions?